Okay, so now we study the HeapSort. Okay, so HeapSort is a sorting algorithm which is pretty efficient, and we have already studied algorithms like insertion sort and merge sort. So, like insertion sort, HeapSort is also a in-place sorting algorithm. Okay, so you do not need more than a constant amount of space outside the main array space. So merge sort was not in-place sorting algorithm. HeapSort is a in-place sorting algorithm. It has pretty good efficiency, and that I'll show later. But before we actually talk about the HeapSort, it uses a pretty efficient data structure which is being used in some other data structure as well. So that data structure is called a heap data structure. So what is a heap data structure? It's a binary heap data structure. Um, is an array object that we can view as a nearly complete binary tree. Okay, so nearly complete binary tree. So it's a binary tree. So every node has two children, and it's a nearly complete. So all the levels are mostly the last level is not necessary to be full. Okay, so heap data structure is actually can be represented as a tree, can be represented an array also. Okay, so it's called an array object. It's an array object that can be viewed as a binary tree. So I'll show you the relation between the array object and the binary tree formation, or the binary tree structure of the same data structure. Before that, we talk about the max heap property. So heap data structure satisfies either of the two properties. Either it is a max heap or it's a mean heap. If it's a max heap, then what happens? Then the parent node is more than the child node's key values. The key of the parent node is more than the child node. Okay, so the key of a node is greater than equal to the keys of its children. Okay, so suppose this is the binary heap data structure, and this is the parent node, and these are its two children. You see that the parent node's key value, which is 16, is greater than both the key values of the children. Okay, 14 and 10. Here, if it's a mean heap, then it will be opposite. Okay, the parent node's key value will be less than the two children. You can see that if you know about binary search tree, heap data structure is different than the binary search tree. In binary search tree, the left child is less than the key value of the left child is less than that of the root, and the key value of the right child is more than that of the root. So if it's a binary tree, it will be like this is 14, so this is 10, and this is 16. This will be a binary search tree data structure's key values. The left child will be less than the root, and the right child will be more than the root. But this is a heap data structure, not a binary search tree data structure. So this property is that the key value of the root is less than the key value of the left and the right child. Okay, so now there is one important thing. As I said, array can be represented as a heap. So given a big large array, we can convert it into a heap data structure, binary tree data structure, as long as it satisfies those heap properties, that the max heap and the mean heap properties. So depending on that, we will convert it into a max heap or mean heap. So see, these are the indices of the array element from 1 to 10, and the first element will always be the root. Okay, root is the first element of the array, so it's 16. Then what about 14? 14 is the second element of the array. Okay, so that is the left child of I. If this is I, then left child of I is 2 times I. So this is I equal to 1. So I equal to 1 here. So this is I equal to 2. Okay, so that is 2 times of 1. And the right child is 2 times I plus 1. Okay, so it's 1, 2, 3. Now see, this 3 are the root, left, right. So this is the root, this is the left, this is the right. Again, for this node, for this subtree, this is the root. Okay, 14. So now 14's 2 times, that's the index position 2. 2 times 2 is 4, that is 8, which will be the left child of 14. And 2 times 2 times 2, that is 4 plus 1, 5, that is 7, will be the right child of 14. Okay, so this is always 2i. If this is the I, then 2i and 2i plus 1, 2 times I and 2 times I plus 1. Similarly, all of them. So this is the heap is formed from this array. So left left child of I, index I, is 2 times of I, the index of that node, and the index of the right child of node at index position I is 2 times I plus 1 position. Okay, so what about the so you can see this is one thing here, like this element 6, 7, 8, 9, 10. So this element, half of the array, is actually at the leaf level. Okay, so these are all leaf nodes. Okay, so now if you try to find the parent of a node, then we just go I by 2. Okay, I remainder 2. So that is like if we try to find out the parent of 9. So 9 is position 6, so it will be 6 divided by 2, that is here 3. Okay, so if we go for 3, that is 7, remainder 2, and so that is 3 again. Okay, so not remainder division. Okay, so this is the way you can find the parent, left child, right child of a heap binary tree. Now this is the left subtree of the heap, and this is the right subtree. Okay, so the left subtree is this one, rooted at 14. The right subtree of the heap is rooted as 10. Now we go for the heap operation. If heap is a data structure, it must satisfy certain standard operations. So what are the heap operations? Two operations. One is that build max heap, which actually produces a max heap from an unordered array. So this is an array, and this is in an orderly fashion to create the heap. So if it's unordered, then from that how we create a max heap. Okay, from this array to this tree structure. Okay, and another operation is a max heapify. Okay, so what it does, max heapify correct a single violation of the heap property in a subtree at its root. Okay, so this is might be difficult to understand what I'm trying to say. It says a single violation at a time. Okay, let me tell you. So suppose this is a binary tree, and sorry, it's a heap data structure, and here I mean, of course, it's a binary tree also. Now assume that someone wanted is kind of a sorted array. So you can see that it's not a sorted array, but it's a max heap property is being satisfied. So the root is always the max heap. So if I want to pick up the maximum element of this array, I always have to build a max heap and then pick out the like a cherry on top. So it's the maximum element. If you want to do min heapification, and then always the minimum element will be in the root. And if you want to pick out mean every time, so you pick out that and then again do the max heapification of this entire thing. Okay, sorry, mean heapification. Okay, so then again you go get the next minimum at the root. So in this way, max heapify or mean heapify, depending on what kind of heap you are using, it can correct a single violation. When I pick this node out, then the root, the heap property will be violated. In that case, I need to redo the heapifications. Okay, so max heapification. So this is so let's see what max heapify does. Max heapify assumes that the trees rooted at left eye and right eye are max heap. Okay, suppose this is the heap. So we first the root is 16, which is more than the children. So it assumes that the left subtree and the right subtree are max heaps. Okay, so this is the assumption. This is important. Left subtree and the right subtree are max heap. Then it checks, so left eye and right eye are max heap if element AI violates the max heap. Okay, initially what I assume that this is a max heap. Okay, then I check that, okay, suppose then I come to this node particularly, probably the I. Then I check, okay, the subtree at this and this are max heap or not. Then I see yes, they are max heap. But then I see what about AI itself, the root node itself. Okay, and then I see, oh, root node is actually less than the children. Okay, can either of the children or both the children. Okay, in this case, this is both the children. So then, if element AI violates the max heap property, that means this is actually violating the max heap property. In that case, what we do, we correct the violation by trickling element AI down the tree. Okay, making the subtree rooted at index I a max heap. What does it mean? It means that if you see that among the root in this subtree, the root, left child, right child, find the largest element. Okay, what is the largest element? Largest element is 14. So then what I do, I exchange 4 and 14, swap them. Okay, so this operation is called max heapify. A2, 2 is the position. Okay, and A is the array. So max heapify A2 means max heapify the subtree rooted at 2. Okay, so at this stage, what I do, I swap, so exchange A2 with A4. Okay, so A2 with A4. So because we find among these three, the root, the left child, which is 2 times the root, and 2 times means the index, and 2 times I plus 1, this is the right child, among them which is the largest. We find this is the A4 is the largest, so we swap with A2 and A4. So this becomes 14, this becomes 4. Okay, so now we see that subtree rooted at 14, I mean at this level, this is now a max heap. But what about this subtree now? Now at this subtree, we have to keep checking till we go to the leaf level. Okay, now we check at this subtree, the this root node is actually violating the max heap property. Okay, so because it is larger than the left child but smaller than the right child, and in a max heap it cannot be, it has to be max of both of the children. Okay, I mean larger than both of the children. Then among them which is the largest we find out, because we call max heapify on A4 this element. Then we say, okay, exchange A4 with A9. Okay, because A9 is the largest. So what I do, I make this one 8 and this one 4. Okay, then again I check, is it is this one satisfying max heap property? We see there are no more children because there's the leaf node. So now this is a max heap. So then we do not need to make this recursive calls. Okay, so this recursive calls will can go on the maximum time if this is for the left subtree until it reaches the the lowest level. Okay, so for the type of trees which are having the minimum the half fill at this level, at the leaf level, so the maximum time this can go on for the size of the tree can be 2n by 3. Okay, so I can show you the calculation how it becomes 2n by 3. I mean the size of this left subtree cannot be more than 2n by 3. So the time complexity of this algorithm will be like Tn less than equal to T of 2n by 3. T of 2n by 3 plus theta of 1. Why theta of 1? Because the fixing the errors like swapping, this is a constant time operation. This takes fixed time, just swapping. So we talked about it earlier when we talked about the RAM model, that a particular step, if you repeat it every time, it takes the same amount of time. And this is just one swap. You can see this is it's a simple operation. So it's a constant time operation. But Tn to the worst case time complexity will be if this left subtree is the largest, any subtree left or right, as long as the tree is half filled in the lowest level, because we do it from the left side for a binary tree. So of course we are actually considering the left subtree. So the time to do the max simplification is upper bounded by for a maximum number of elements, that trickling down will continue. Like here we trickle from this to this, from 14 to 8, then from 8 to 4. In this way you can trickle down maximum up to 2n by 3 height, because that is the worst case height of this left subtree in a binary tree. Okay, so I'll continue explaining this to you. Okay, so after we talked about the max heapification, we decided that we'll discuss about the complexity analysis of the max heapification algorithm. So maxification runs in order of log n time, and I'll tell you here why it is order of log n time. Okay, this is important. So so this is said worst case of the maxipify occurs when the bottom level of the tree is exactly half full. Because it's binary tree, it will be filled from the left side. So if the bottom level of the tree is exactly half full, means the left subtree has one extra level than the right subtree. Okay, so then what is the height of that? Let's see. So this is the standard way of representing tree in the literature. So this is the root node. Okay, so this is the root node, and this is the left subtree, and this is the right subtree. Okay, so the left subtree starts at this node, and then right subtree starts at this node. So now the number of nodes in a binary tree is the the maximum number of nodes in a binary tree is of height h prime is every level, like first level 2 to the power 0, second level 2 to the power 1, 2 nodes, third level 2 to the power 2. In that way, if up to h prime is the height of the tree, then at that level 2 to the power h prime. Okay, so remember this 2 to the power h prime. So this is the number of children at each level, number of children each node has, and to the power the height of the tree. So at a particular height, the number of nodes is 2 to the power the height of that of that level. So if you add them up, it becomes, because this is actually 1, so this, if sum up, it becomes 2 to the power h prime plus 1 minus 1. For the root level there is one node only. Okay, so this is the maximum number of nodes in a binary tree. Now you consider only the right subtree first. So the right subtree starting from the this right child of the root. So if the height, suppose the height is h. So you can see if we count all the nodes in the right subtree, it will be 2 to the power h plus 1 minus 1. Okay, the whole thing. Okay, from here. So number of nodes here is 2 to the power h plus 1 minus 1. Okay, so assume that is, we represent it with a k. Now you consider left subtree. Left subtree, we said the bottom level of the tree is exactly half full. So the left subtree's bottom level is full. Okay, the right subtree does not have any node in the bottom level. So consider the left subtree. If we consider up to here, okay, so this is actually same as the right subtree. Okay, so if there are k nodes here, there are k nodes here also. Now what are the number of nodes at this level? We know that the number of node at a particular level is 2 to the power that the height of that level, which is one level more than one, height is one extra than this right subtree. So it's h plus 1 the height. So the number of nodes in this level is 2 to the power. So this, now we are kind of summing up all the nodes in the left subtree. So this is 2 to the power h plus 2 minus 1. Okay, 2 to the power h plus 2 minus 1 is the this whole subtree will have. Okay, so now if we try to solve it, 2 times 2 to the power h plus 1 minus 1. Okay, so if we take 2 outside, the parenthesis is 2 times the whole 2 to the power h plus 1 minus 1. We represented it like this, 2 to the power h plus 1 minus 1, and then because it's 2 times 1 is minus 2, we subtract 1 out of, we add 1 to make it 2 to the power h plus 1 minus 1, this expression. Okay, for this expression we can put a k. You see, this is the height, the total number of nodes in the right subtree. So if the total number of nodes in the right subtree is k, the total number of nodes in the left subtree with one extra level completely full for the left subtree is 2 times k plus 1. Okay, so I hope you understood this. Now you see total number of nodes in the tree. The whole tree is what then? It's the root, this node, plus the number of nodes in the left subtree, plus the number of nodes in the right subtree. Okay, so this is root plus left plus right. So I should write that the number of nodes in left subtree, number of nodes in right subtree, but I hope you understand. So number of root is 1, number of nodes in left subtree we calculated here to show that it's 2k plus 1, and number of nodes in the right subtree is k. Okay, so this is actually total 2k, 3k plus 2. Okay, this is the number of nodes in the whole tree. Okay, so the ratio of the nodes in left subtree and the whole tree. Okay, left subtree and the whole tree. Why we just do left subtree? If you remember the max simplification, if there is an error, suppose this is A, this is B, this is C, D, E, F, G, we kind of every level we go down until we go till the the leaf node. So we only check in one subtree because the max simplification is correct with respect to one subtree. Pick the largest node in the subtree and go on checking till the leaf level. So now the ratio is 2k plus 1 is the number of nodes in the left subtree divided by 3k plus 2, which is the number of node in the whole tree. So for sufficiently large k, I mean if k tends to infinity, this will turn into 2 to the power 3 in the limiting case. Okay. So that is the reason we say that it's 2n by 3 number of nodes in the left subtree compared to the whole tree. Okay, when the left subtree is completely full, the lowest level, or we can say that the lowest level of the whole tree is exactly half full. Okay, so now if we talked about this, the complexity of the maxipify will only focus on one subtree and go till the end. Okay, and if the left subtree is exactly half full, that will be the worst case time, because then you have to consider all the nodes in the left subtree till the lowest level. So the complexity is upper bounded by t2n by 3. It's a recursive call every time you go on calling it until you find that it's you reach the leaf node and there is no children. And theta 1 is the time to do the swapping. So that, as we said, it's a constant time operation. So if we put the Master's theorem case 2, the solution of this is becoming Tn equal to big O of log n. Okay, so this is straightforward. I hope you will try to understand this kind of properties of the tree is important to do a lot of deduction. That's why I'm trying to show you every step, and this is important for your understanding.